All right, hello. So I received my first question on exercise 12.1. And looking at their code, I think the issue is just a matter of them making the problem a lot harder than it is. So I thought rather than try and say debug their code, is I'm just going to essentially solve it starting with my solution to exercise 7.4. All right, so what I'm going to try and do is just walk through the solution and hopefully show you that it's really not all that bad, right? So to try and connect the dots. And so basically in exercise 12.1, okay, we're going to resolve exercise 7.4, where in exercise 7.4 we had used F0. Here I ask you to use interp 1. So if I go back to exercise 7.4, this is our azeotrope hunt problem. So you're given the temperature, along with Antoine constants and model parameters for activity coefficient models. But basically we're asked to solve for the composition at which alpha is equal to 1. So you're given the temperature, so P1 set and P2 set are known. On the right-hand side, my only unknown is x1. We want to solve for the value of x1 so that alpha is equal to 1. Or equivalently, how I solved it is I solved for when log alpha is equal to 0, since the log of 1 is 0. Okay. So before I started to record, I downloaded my solution from the solution manual, which I will bring up here. Okay. So first thing, let's look at the solution from 7.4. And then we'll run it, get an answer, and we'll see how we'll update it using interp 1. And so I have a function with no inputs, okay? And so basically, I have this helper function, log relative volatility, which just for a given x1 value returns the log relative volatility, okay? And then I'm using F0 to solve from the log relative volatility is 0. So I'm using log alpha. Log alpha is going to be equal to 0 at my azeotrope. Okay, so F0 will iterate on values of x1 until log alpha relativity returns a value of 0. Okay, cool. So everything should be vectorized because F0 prefers everything to be vectorized, well, especially since we're adding fplot to the mix. Okay, but log relative volatility takes x1 as an input. Temperature is defined. My Antoine constants are defined. So with those Antoine constants and that temperature, I calculate the vapor pressure of component 1 and component 2, or the log vapor pressure. And since temperature is just constant, then the vapor pressure would just be constant. Declare our Van Laar parameters, and once we have those, you can pass it to a Van Laar function, which takes our Van Laar parameters and x1 as inputs. Okay. There's my Antoine function. Here's my Van Laar function, which appears to be vectorized, so that it takes my Van Laar parameters and x1 as an input and returns log gamma 1 and log gamma 2. Right? So everything's nicely vectorized. Okay, so if I were to minimize this, let's call this say x1f. Okay, so the value of x1 I would calculate using this method using F0 would be, so water butanol ezio, right? I run it, has no inputs. There's my plot. Beautiful, and I solve for, or I find that the composition at which my azeotrope occurs is 0.7940 wolfracs. Okay, cool. So I'm going to close that. Okay, and what I'm going to do is I'm going to go back up to my editor. I'm going to save a copy. Okay, let's call this interp. Okay, and so I'll update my function signature. Add the interp to it. And so let's resolve this using interp 1. Okay, so the solution really isn't all that bad. So remember what I'm doing here is F0 is going to iterate on values of x1 until I solve for when log alpha is equal to 0. How I'm going to use interp 1 is rather than iterate on values of x, I'm going to create a vector of x values. I'm going to calculate log alpha each one of those x values. So I have a vector of x1 values, a vector of log alphas for each of those x. And then I'm just going to interpolate to solve for when the x value for which log alpha is equal to 0. Okay. So I'm going to create x1, an x1 vector at which I will compute alpha. Okay. So I'll do a big x1 since it's going to be a vector. I'll use a linspace. I can use as many data points as I want. Of course, the more data points I use, the more accurate I would expect it to become. So I'll use, say, 100 data points. I'll just use standard lint space. Okay. Then we'll evaluate alpha at each x1 value. Okay, so remember, log relative volatility is already vectorized, so we'll do log alpha is equal to ln relative volatility, and we're going to pass to it x1. It's already vectorized. We want to compute log alpha each one of those x1 values. All right, so there it is. Okay, then last, let me comment out f0. Right, we don't need that. So then finally, let's solve for x1 at which alpha is equal to, well, log alpha is equal to 0. Okay, how are we going to do that? Okay, well, if you can't remember how to use interp1, all right, you just type help interp1. Okay, and so remember our basic call will be, so they listed as x comma v comma xq, right? But if I just look at the example, right, I have, say, two vectors and xq, right? So I'm going to solve for the value of v, in which xq is that value, right? So if I think about this case here, I know the value of log alpha, right? And I want to solve for x for when log alpha is equal to 0. Okay, and so actually we'll write this then as, so res, the x1 value at my azeotrope would be, okay, interp1, my x value will actually be log alpha, okay, my y or v variable will actually be x1, okay, and so essentially this is my independent and dependent variable. And I want to solve for x1 at which log alpha is equal to 0. Bam. Okay. That's all it is. Okay. And I just brought this up because oftentimes the issue with using interp1 is just remembering the order of all the variables. So remember, help interp1, will bring up an example that you should be able to follow. Okay. So if I clear screen, let's do x1. So we see my answer before, 0.7940. I'm going to call this x1 lin, because this would be using linear interpolation since I didn't specify anything. And I get beautiful plot, and I actually get the same exact answer. Right? I'm using 100 data points, so I'd expect that it should be pretty good. Okay, but that's it. I mean, just to have fun, let's see what happened if we use 10 equally spaced points. Okay, so if I use linear interpolation, well, I'm still getting 0.7940. Okay, boy, am I missing something? Okay, if I use 5 data points, still 0.7940. Oh, it's because I'm a fool. I'm calling the wrong one. So x1 lin, I want to call interp. Sorry about that. Okay, so when I use just 5 data points using linear interpolation, I get 0.7793, 50. Now I'm up to 0.7939. Okay, so I'm getting pretty close. 100. All right, 0.7939. Right, I'm pretty close. Right, 0.7939 is pretty darn close to 0.7940. Let's see if we're to make it 1,000. Yeah, all right, 1,000. I'm getting it exactly. Okay, but just to have fun. So if I bring this down to say 20, I'm 0.7936. Right, still you're pretty darn close. All right, so if you were to round this to the 3rd decimal place, they're exact. But you could try other things. So, what would happen if I tried to use p-chip? Okay, so if I use a piecewise cubic Hermite interpolating polynomial, I get 0.7940. Right, and so that does the trick. If I use 10 data points with p-chip, all right, 0.7938, all right, you're still really close. Okay. But that's all that it takes to update your code from Chapter 7 to get it to work for Chapter 12. Right? So here I just eliminated F0, and added just those simple 3 lines of code. Okay, that's it.